Hi, my name is Jabulani. I am recording this video just to show you how to do the manual calculations of independent sample t-test. And some are saying, what's that? And for those who know, and in most cases in research and for statistics, we would want and like to compare if there's a significant difference between conditions, between population groups, among other reasons. And then students often get confused on which one to run between the two t-tests, the one for dependent samples t-test and the one for independent samples t-test. So the one that I'm showing you here now is when two groups have been used in the process of data collection. So we have two groups or two conditions, mostly from an experimental design, whereby sometimes and often we have a treatment group and we have a control group. So we have we assign participants in a treatment group and we assign participants in a control group. When we have such a scenario in the case, that is when you run independent sample test. But sometimes we, excuse me, sometimes we use the same sample whereby we measure before and we measure afterwards. So when that happens, so we select, we assign to whatever conditions, and we measure the same group of people or participants um, before an intervention, for example, and then we measure after an intervention as well. So when the same group or when there's matching that was involved, that is when we make use of dependent samples t-test. But this video is focusing on independent samples t-test. Like what I just said, my name is Jabulani Chitanga, and I have other videos. So there is a video that is available for you if on my YouTube channel, whereby you can follow how to do the manual calculations for dependent samples t-test. There are other videos also on how to do that in Excel. So some may ask, but why are we focusing on the manual calculations instead of kind of being in line with technological advancements? I am aware that, but I think it is important that students also have knowledge of doing the calculation so that they see what happens with the equations and the formulas that comes with the statistical test. So I'm going to be showing you how to run the calculations. But before I get that, this just slide to show you the difference. And actually, when you are faced with such a situation, uh, you should know which test to run between the two t-tests. So dependent sample t-test and independent sample t-test. So I think you'll be fine with that. But the focus on the calculations is because most students find that challenging, or maybe it's not easy for many. So that is why I'm providing this kind of a video, so that we help each other and then we become whatever that we want to become. But obviously, in most cases, the questions ask you to test for hypotheses if there is, for example, a significant difference between a treatment condition and a control, between the treatment group and the control group. So you obviously start by stating the hypothesis, which is the null hypothesis, alternative hypothesis. You can read that. I don't want to focus much on that. And then the second step, mostly, there can be other steps depending on the textbook that we are reading. The second step, obviously, is to locate the critical region using the critical value. So in the last pages of most textbooks, there are critical tables, critical value tables. Are they called like that? Yes, they're referred to as critical value tables. So there's one for t-test, one for correlation, one for F. There's Z-score, normal distribution, among others. So there is a way of identifying that critical value that I mentioned. I'm going to show you as well. So we are going to compare the critical value and the t statistic that we've obtained to make a decision whether we reject or fail to reject the null hypothesis that we've stated here. And then every time you have a significant difference, you proceed to calculate the effect size. Um, in most cases, we use the estimated coins D, but there's also eta squared that can be used depending on what the question is saying. So I'm recording this for those who are like second year, third year, even some postgrad who are making use of statistics, or maybe with the modules that involve statistics mostly. So this is the formula for T for independent samples t-test. So this is the T. In the numerator, we have the sample mean 1, sample mean 2, minus the population mean minus the population mean 2. In the denominator, we have the estimated standard error. So the numerator is quite easy. Allow me to use that word. And then the denominator is whereby we need to kind of split, because the formula for estimated standard error is the pooled variance divided by N1. They mean that the sample size for group 1, for example, a treatment group, and then the pooled variance divided by the control group, if I can say so. So we add that in the square root, pooled as in, excuse my pronunciation, P-O-O-L-E-D, not the P-U-L-E-D. I don't know how you pronounce it, but anyway. And then, but now we cannot complete this without that pooled variance that we need, because the the formula for estimated standard error needs this. So we need to calculate the pooled variance first. So we calculate the mean, the pooled variance, but before we calculate the pooled variance, we need to calculate the sum of squared deviation for each of the groups. So for group 1 and for group 2, divided by the degrees of freedom for group 1 plus degrees of freedom for group 2. So when we do that, we can complete the formula. So I've kind of so we can follow these steps, like you calculate the mean, the SS for each group, the degrees of freedom for each group, and then after that you complete the pooled variance, and then the estimated standard error, and then the t statistic. So follow this. I think you manage if you do that. But now it's still difficult for some. Let us show you. I'm saying us, we are on the same side. So what I did to make this video not very long, I excuse my writing. I wrote, so remember the first, what we need to do first is calculate the mean for each group, and then the SS1, SS2, the degrees of freedom, and then that is going to help us to identify and calculate the pooled variance. Let me take a pen here. Let me use another color, or must I use red? Okay, let me use red. So I'd want to kind of say, okay, everyone knows how to calculate the mean, but the mean one, so you add each score, you add all the scores and divide by the number of scores in a distribution. So 10 plus 8 plus 7 plus 9 plus 13 plus 7 plus 6 plus 12. And then we divide that by 8. So you get 9. You do that. And then for the second, the control group, 7 plus 4 plus 9 plus 3 plus 7 plus 6 plus 10 plus 2. You do the same, divide by 8, and then you get a 6. And then the degrees of freedom for each group is n minus 1. N minus 1. So we have 8 scores in a distribution, 8 participants actually. So it's n minus 1, that's 7. And then the second one is 7. But at this stage, in most cases, we give, I'm saying we, because I'm on the lecturing side. In most cases, we give you equal number of participants in a study, but it's possible that the other group can have 7 participants, the other group can have 8 participants. And before I forget, one of the students say, but you lecturers are not fair. You send us, you give us something, but when you give us an assessment, you arrange the scores in a different way and manner. So I'm just saying, for example, this, we can give you like something like this in a vertical way and manner. So this is the control group. The scores can be in this way. It doesn't change anything. So it's the same as this. So I'm just saying this on record so that we don't have people who may end up complaining that we didn't teach them quite enough. I'm speaking on behalf of N1. So this is our video. all of us. And then, so we have the mean, the degrees of freedom, degrees of freedom. So here we are set for the calculation of the pooled variance. But what we don't have is the sum of squared deviations. So the formula for that is sum of squared x's minus sum of x squared, sum of x squared divided by n. So we do that for each group. So for the first group, for example, it means that sum of squared x's, it means 10 squared plus 8 squared plus 7 squared plus 9 squared plus 13 squared plus 7 squared plus 6 squared. So it's 100 plus 64 plus 49 plus 81 plus 126, something like that. So when you do a search, you get 692 minus the sum of x. So it means we add 10 plus 8 plus 7 plus 9, you get 72. So we square that, divided by the number of scores in that distribution. Sorry, that's n. So when you complete that, you get 44. Okay, that's SS for group 1. We do the same for the second group. So it's 49, 16 plus 81. And then if you get 344 minus, in the same way in main, 48 squared divided by n. If you complete that formula, 56. Okay. Let me write, actually, let me write 8 here. And n, actually 8, like this. So 56. So you see, this 44 is SS1, and then 56 is SS2. So let's complete these pooled variance. So it means 44 plus 56 divided by the degrees of freedom, 7 plus 7. 7 plus 7. If you complete that formula, you get 7.14. So it's 100 divided by 14, 7.14. So this is the pooled variance. And then we're not done. We're not done. So now the formula for estimated standard error is that pooled variance in a square root divided by n, so which is actually in a square root. Remember, 7.14, 7.14 divide by not degrees of freedom, but by n, and 1 plus 7.14. So please don't confuse that when you do the division, and don't forget the square root. Let me write here so I don't have space. So it's 8 into 7.14, you get 0.89, and then 0.89. So if you add the two, you get 1.78. Like what I've just said, don't forget to take out the square root. So square root of 1.78, the answer is 1.34. 1.34, like this. So remember now, let me check if I wrote here. Where did I? Yes, I wrote here. So this is our formula for, okay, excuse my writing again. So it means now we need to complete. M1 is 9, remember, minus 6. And then this is going to be 0 because our now hypothesis mentioned that there's no significant difference. So it's going to be 0. Don't have to worry about that. And then the estimated standard error that I've just calculated here, 1.34. So we write 1.34 here, 1.34. If you complete that, you get 2.24. So T is 2.24. But now, how do you know if you need to, if you reject or fail to reject the null hypothesis? I forgot to mention that we are testing at 0.05. So that is given in the assessment. We are told that use significant level of 0. Sometimes you write as 0.05. Sometimes you say 0.05. It's almost the same. And then when do you know how to use two-tailed or one-tailed? So when the question just said that test if there's a significant difference between the two groups, you make use of two-tailed testing. But when the question mentioned that control group is going to have higher scores than the treatment group, I'm just saying, or vice versa. So you make use of one-tailed testing. So in the last pages of a textbook, when you check the critical value, that is when you make use of that tailing. But for this one, it is two-tailed, so it informs us when and where the critical region is starting from. So if you check 0.05, the degrees of freedom um, for for independent t-tests is n minus 1 plus n minus 1. So which is 14, okay. So it's 8 minus 1, that's 7, plus 7, 14. So you check under degrees of freedom 14 under 0.05 in a two-tailed draw. So when you do that, you're going to obtain a critical value of this side 2.14, 2.14, and negative 2.14. So it's two-tailed, so it doesn't matter, is it negative or positive? It is possible that this value can be negative, but if it's two-tailed, it's almost ignored. So 2.14, excuse me, I want to write 1 here, 2.14. And then now, the shaded, it means that if you obtain a score that is greater than 2.14, reject the null hypothesis, like ours. Ours is somewhere here. So this is 2.14, it falls in the critical region. So we reject the null hypothesis and conclude that there's a significant difference between the treatment group and the control group. That's what you do. And when that happens, you proceed to calculate the effect size. In most cases, estimated coincidence is used. This is the formula for that, M1 minus M2, which is 9 minus 6 divided by the square root of the pooled variance. Remember the pooled variance that you obtained is 7.14. If you complete this, this is a 6, by the way. Am I writing again? So you get 1.12, 1.12, which is a large effect because the value of t-test, just tell you that t-test is 2.24 or 5.76, whatever value it is, but we need to check and understand. Let's say we have introduced an intervention. We need to check if that intervention is a small effect, medium effect, or large effect, but you can read around that. I think I've managed to help. And also you can use the eta squared, whereby you square the t that you have obtained, 2.24 squared divided by 2.24 squared plus the degrees of freedom, so of which is 14. So if you complete that, you can express it as a percentage, the kind of variance accounted for almost. So that's that. I hope I've managed to help. I want this to be clickable, but anyway, you can use my name to search for the other videos that I've shared. And like what I've just said earlier, you can make use of Excel, I don't know how you pronounce it, to do the same. So there's data analysis tool pack. You can watch one of my videos as well on YouTube, and you can activate and follow whatever that I'm showing there. But yeah, I wish you all the best in your assessments and exams and whatever assessments that you may have towards understanding of how we can resolve mental health issues using psychology and science. So thank you so much. I wish you all the best.